All right. Bonjour. Hello. Thanks for coming along to my talk. My name is Noel Welsh. I work at two places, which are both Scala consultancies, which serves the UK and European market, and Inner Product, which is working in the US. So this talk is about teaching Scala. I want to give you a little bit of background and motivation, and then an overview of what's in the talk. So let's start with where I started, which was teaching Scala, which I've done for about 8 years now. And I discovered from teaching Scala that it's a big language, as I think we all know, and it was difficult the first few times I did it. I had to find some structure in how I taught Scala. But not only was it like the content that we taught, it was also the teaching itself, which I realized was quite a distinct skill to programming. Although you may be a good programmer, that doesn't mean you're a good teacher. I think we've all had experience of teaching, so if you pull someone off the street, they may do a better job than if you pull them off the street and ask them to do some programming, for example. But although the floor is perhaps higher, it doesn't mean that the ceiling is lower. There's still a lot of improvement you can do in your teaching. The other thing is that I believe teaching is an undervalued skill in our industry. This room should be full. And the reason I say that is I think teaching is a really essential part of what a lot of us do in our jobs, and we maybe don't appreciate that. So if you're a senior developer, it's probably an explicit part of your job description that you'll be teaching or mentoring juniors. So it's something that you need to do to improve the output of your team, improve the quality of your team, and that's really your role. There are other things where I think teaching is important. For example, Scala Bridge, where we teach people who are underrepresented in the tech community to try to get them into the Scala community. And I think that's a very valuable thing that we're doing. And finally, we teach ourselves. The industry is constantly changing, new things are happening. We've got Scala 3 coming out next year, for example. And so we really need to... Sure. Oh no, that's okay. I'll just keep talking for a little bit. So the skills for teaching are actually very useful for learning. And so if we can use some of these skills, we can use them for teaching ourselves, for learning the new things we need to learn to stay relevant as a developer. So my talk, I'm going to cover 5 tips for teaching. I try to make these all very actionable things you can take away straight away and then use in your own teaching of Scala. And then I'm going to give you 5 further resources where you can go to get more information if you're interested in exploring further. A little bit more structure on what we're talking about here. So the first thing when people talk about teaching programming on the internet is they always argue over language choice. You'll see people saying you should be using Python or you should be using JavaScript, that kind of thing. Well, I have opinions on that myself, but for this talk, it's a given that we're talking about Scala. My opinion is that functional programming is a much simpler model you should use if you're teaching beginners, but it's not really relevant to this talk. So what I will be focusing on instead is curriculum, which is what you teach, and pedagogy, which is how you teach it. Okay, so those are the 2 main things I want to talk about. So let's get into it. So 5 tips for teaching, and tip number 1 is this idea of a notional machine. Possibly something you haven't heard of before, so let's get in and describe what that is. So teaching a notional machine is something you need to do particularly for beginners, and it's the difference between giving them understanding, a model they can understand and code and work with, or what we call cargo culting, so basically copying and pasting code without any real understanding. And when I look at a lot of the online resources for learning to code, I see a lot of what I think is falling into the cargo culting. Just have this sort of area, where people are not being given a model of the machine, so they can't really understand what the code is doing. They're just copying and pasting and making small tweaks. So a notional machine is some kind of simplified or abstract machine model that explains the programming language semantics. When you hear that, you probably think of something like a sort of register machine or something with a stack, kind of a simplified CPU, registers and call stack and that kind of thing. But in functional programming, there's a much simpler machine we can use, and that is substitution. So what is substitution? Well, let's have a look. So let's say we have this expression. I ask this occasionally at various different places. Can anyone tell me what a plus a is going to be? Sometimes we get good responses, sometimes we don't. Let me say, they're very reticent to answer this in the US, so let me show the European education system is much better. You can tell me what a plus a is. Yes, 2, okay. And how do we know that? We know that because we can basically do substitution. Whenever we see a name here, we can substitute in the value that it is bound to. So we see a, we can substitute in 1, and we get 1 plus 1, and then as we know from primary school, 1 plus 1 gives us 2. Okay, and then we can do the same thing, would you believe, for b times b. We have the name here bound to the value 2, substitute in 2 times 2, and of course we get 4. Right. So that's very simple, that's primary school stuff, so what? What's the big deal? The big deal is you can extend this much further. You can do substitution for methods. So with a method, you're just substituting in the parameters, renaming the parameters if necessary, depending on scoping, and away you can go. So whenever you have a method call, you can substitute in the method body, substitute in the parameters for the values they take, and just go and do it. So it works for method calls. It works for types as well. You can perform substitution at the type level. So if you have like a list or list A, and then you use int, you have a list int, you can substitute int for A and do that consistently. And in fact, it works anywhere that you have pure code. So as long as you don't introduce state, substitution is going to work. That's nice. And the other point is, it's really easy. I suspect some of you are looking at these slides and going, why am I telling you about substitution? It's so obvious. That is 100% the point. The point is it's easy. We don't want to do complicated things. Why do complicated things like introducing register machines and stacks that you have to maintain when you can do something easy, substitution, which you learned about in primary school? That's 100% the point. And for me, substitution is not just the point of using this as a notional model, but it's really the point of the entire functional programming enterprise. It's the intellectual basis that everything rests on. So that's why we care about immutability. We don't care about immutability for its own sake. We don't make code immutable just so we can say it's immutable. We care about immutability because it means we can use substitution as a reasoning principle. And similarly, that's why we care about things like monads, for example. Why do we model effects using monads? Because they allow us to maintain substitution up to the point where we run the monad. So when I think of substitution, for me, this is really the entire point of functional programming. It's maintaining this really, really simple model, this primary school level model of reasoning about code in the face of all the complexities that real code has. That's why we care about it. So substitution is, yes, very simple. That is 100% the point, but it really is, to me, the whole thing that underlies functional programming. That's why we care about these things, so we can use this really simple tool of reasoning to reason about really complicated programs. All right, so that's substitution. Just a sec. It's annoying me. Okay. Now, tip number 2. This is programming strategies. This is something that I think is quite unique to how we teach programming, so you probably won't find this anywhere else. Pay attention, if you're not already. The idea behind programming strategies is we can make programming into a systematic and repeatable activity. So this means that students, or indeed anyone, I use these strategies myself in my programming, have a well-defined process to take them from a problem to a solution. It's something I really saw people struggle with in introductory courses. When I learned programming in my undergraduate, the first language we used was C. I came in having done quite a few years of Pascal programming already, so I was used to how things worked, but I really saw that my fellow students who didn't have that background didn't understand how to take the language constructs they were taught to actually solve the problems they were given. So there wasn't a link between the language constructs and the problem solving. And program strategies provide this bridge for us. They're like design patterns, but they differ in a number of ways. They're wider in scope than what we talk about. We're not just talking about sort of design things. And they're also more formal, more kind of formulaic, more systematic. We've identified 10 strategies. I'm going to focus on 3 here. And those strategies are algebraic data types, structural recursion, and following the types. I'm just kind of interested. Who's heard these top 2 terms before? Algebraic data types and structural recursion? Just want to see. Okay. There's a lot of hands going up. Okay, so this will be interesting to see if it matches your understanding. Let's go on to algebraic data types. The key idea with algebraic data types is that whenever the data is described in terms of a logical AND or a logical OR, then once you've got the data description, the code that implements it follows immediately in an entirely formulaic way. So let's see what I mean. Go, for example, if A has a B and a C, then we can immediately write final case class A, that's a B, and a C. Right? That's the direct encoding in Scala 2, of this statement. Of course, different in Scala 3, we've got enum. If you want to know why your case classes should be final, I believe that handsome gentleman in the audience there will be telling you at his talk. So similarly, if you have A is a B or a C, then the way you encode that in Scala, you actually have a few little options, but sealed trait, and then 2 case classes extending it. You could use like a sealed abstract class. You get basically the same thing. It's not worth talking about the difference. Again, that's the direct encoding in Scala of that statement. So let's see an example. If we say a list is a pair or empty, well, we have this logical OR here, so that we know we need to use that OR pattern, and we can immediately write down sealed trait list, final case class pair extends list, final case class empty extends list. And that's just taking the pattern we had earlier and substituting in list pair and empty for A, B, and C. Then let's say a pair has a head and a tail, and we have the logical AND here. And we can just go and use the AND pattern we saw earlier, head and tail, and we need to put types on this. So we say head has a type of A, and tail has a type of list A, and we need to do a little bit more work. We need to introduce the type variable, and then we have head type A and tail of list A. So it's all very formulaic. Some of you might be looking at this and going, could this not be covariant? Yes, it could be. I've just gone for simplicity here. I don't want to explain covariance and invariance and all that kind of stuff. So if you're wondering that, that's what I'm doing. If you're not wondering that, that's absolutely fine. You don't need to talk about covariance and that kind of stuff. All right. So this is a way we've been able to derive this data structure, which is very similar to the built-in list in Scala, just directly from that description. All of this code follows immediately from the description we were given. No thinking required. Let's move on to structural recursion. So structural recursion is in some ways a sort of inverse of algebraic data types. Algebraic data types are about building data. Then structural recursion is about transforming an algebraic data type, or kind of tearing it down and maybe building something new. And the rule here is any transformation you want to write on an algebraic data type can be expressed using structural recursion. That's not saying you have to express it using structural recursion. There may be some helper methods like map and so on that do a job more simply for you, but you can use structural recursion to do this. So this is great for like junior developers. They don't know the APIs yet, they can just kind of bang out code and get something working, and then you can help them clean it up, make it a little bit shorter, use more of the built-ins. So, okay, that's nice. What is structural recursion? Well, 2 ways to implement it in Scala. Because as we know, Scala has many ways to do things. And we can do it in terms of pattern matching or polymorphism. I don't want to show both, it just takes too much space, and I don't think it'd be really useful to you. So I'm just going to choose pattern matching for my examples. It's probably more idiomatic in an FP world. Sometimes people from an OO background prefer to use polymorphism. You get the same goal. There's slightly different trade-offs for the 2 of them. It's not really that important for this discussion. So, structural recursion has 2 patterns which match the two patterns we saw for algebraic data types, the pattern for the or and the pattern for the and. So when we say when A is a B or a C, well, we just need to handle those cases. We have an A, we match on it, we say what we're going to do if it's B, what are we going to do if it's C. So structural recursion gives us all of this left-hand side here, and then the right-hand side, question marks, this is the problem-specific part. It's the bit that we have to figure out for ourselves, unfortunately. I have to do a little bit of thinking, which always disappoints me. Then the other pattern we need to answer is if we have the AND pattern, if A has a B and a C, well, then in that case, we pull the B and the C out, and maybe we use them on the right-hand side here. So those are the two patterns that match the two patterns in algebraic data type, AND and OR. Very simple stuff. There's one important thing we need to add in here, and that's the case in recursion. So we get the structural recursion name from. That tells us when the data is recursive, then the method is also recursive. This gives us a little bit on the right-hand side for free. So, for example, when we talked about the list, we saw the tail here. The tail is a list, so this is where the data is recursive. So if we're writing structural recursion on a list, we know that we're going to have recursion here on the right-hand side. So all of this code comes directly from the structural recursion skeleton. It's not something that the author has, you don't think about when you're writing this. All you need to do is work out what the base case is and this kind of incremental bit. The recursion is given to you, something that people allegedly struggle with in programming is recursion. Structural recursion, you don't have to struggle with programming. You don't even have to think about it. It comes directly from the pattern. All you have to think about here is what's the little step you need to do to take from the recursion to go to the next answer. So it's very simple. Still, we do have bits that we need to figure out ourselves, these question marks. And so how do we complete these? And that's where the final pattern comes in, following the types. So this is another tool we can use to guide us to a solution. Just in the way that the Force guided Luke to destroying the Death Star, we can use the types to guide us to destroy our programming problems. And the way we follow the types is we work out what is the goal, what's the type that we're trying to generate, what is available, what are the things we have in scope that we can use, and then we basically just assemble this jigsaw, this pathway through the types. So you've probably done this before. This is just giving a name and a bit of a formal process to something that I suspect most of you have already done. So let's take a look at map. So we've been tasked to implement map on list. This type signature just comes from map. This is given. This is a given. That's what map is. The first thing to notice is we're transforming an algebraic data type. So immediately, structural recursion, bang, we get this straight away. Now we've forgotten one thing here. We've got the recursion rule. So in fact, we can get this. We know we've got recursion here. And now we need to fill out the question marks. Now we're ready to follow the types. So let's look at the empty case first, because it's the simpler one. First thing is to find the goal. And the goal is given by the return type here, list B. So that's our goal. Make a note of that. Goal is list of B. Then we say, okay, what do we have available? Oops, skip too quickly. And we see in scope we have f, function from A to B. And we also have the constructors. So we shouldn't forget the constructors are always in scope, and they have these types. Empty goes list of A, pair goes A to list A to list A. And when you look at this, and we look at the types, we want to get list of B. Well, we have nothing of type A to apply this function to, so we can't use it. We can't use pair similarly because we don't have anything of type A. The only thing we can do is call this constructor. That's the only possible thing we can do. So in this case, that's what we have to do. Empty goes in there. We can't write this code incorrectly. The types make it impossible for us to get this case wrong. Now let's look at the pair case. Once again, got the same goal, list B. What's available? Well, we have F again. We have the constructors. And here we have some additional information, which is the head, the tail, and the recursive call that we got. So put those in as well. Head type A, tail list A, and tail map list B. Now we have a few choices here. We could, in this case, implement it in 3 different ways. We could return empty, which probably seems like the wrong thing. We could return just list of B, which probably is the wrong thing as well. But what we can do, maybe that's sort of the biggest result we can make, if we know that we have firstly head of type A, and we have F, which goes A to B, where we can apply this function, getting a new value of type B, and then we can put this value of type B and the recursive bit into pair to produce a list of type B, and that is the correct solution. The final bit we have left with is just this recursive call, what goes in here, the parameter. I'll just go through it very quickly. The goal here is given it, we need a function from A to B, and we only have one available, F. So there we go, we're done. So that's how the types guide us to implementing this function. It's a very simple example because I wanted something that fits on the slide and something that's familiar, but you can use this in much larger cases. And we can see that there was very little room to go wrong. Once we had these tools available to us, got most of the way structural recursion, then we could follow the types, and for the empty case, we had to get the right answer. And for the case of pair, there were 3 possible solutions, but it was fairly obvious that 2 of them were incorrect. So this way we can make programming a systematic, repeatable enterprise, something that people can do much more efficiently than they currently do. All right. So I've talked a lot about programming as such, but I want to emphasize that coding is more than coding. Programming is more than programming, particularly when teaching beginners. There are many other skills that they need to have. For example, they need to know how to debug their code, how to debug their errors, which is more than just debugging their code. And they need to know how to use their tools, like their editors and version control and so on. For example, who has ever had Scala C say this to them? I have expected type A but got type A. And that was my response the first time this happened. I didn't have a clue what it meant. It's got a little bit better in recent versions. At least tells you that there's A's that come from different places. But still, it's not a great error message. And then you might have Git say detached head state. Does this mean you're some kind of Edwardian ghost wandering around with your head tucked under your arm? I don't know. Maybe it does. The point is, there's a lot of implicit knowledge that we don't normally teach as part of programming that students need to have. They need to know how to read these error messages. When Scala C says some random garbage, what does it actually mean? Can we translate this into a form that is meaningful? And similarly for Git, when it has its famously terrible error messages and its famously poor user interface, how do we actually use this effectively? So there's lots of knowledge here that we don't normally consider to be part of programming per se, but it's really important. How do you use the editor efficiently? How do you get around code? Now, one way we can solve this problem is we can create courses that teach this. That's fine, but if, like in the context of teaching someone Scala, you probably don't want to take a 6-week detour to discuss editors and version control and so on. So there's one way you can do this, teach this implicitly, and that is to do live coding. Live coding is great for doing this. And you may be thinking, oh, I hate live coding. I don't want to do that because I definitely can't think and type at the same time. I'm going to make loads of errors. That's 100% the point. The point is to make these errors. Get these funny compiler error messages show up, and then you demonstrate error recovery to the students. You show them you made a mistake. So when you're making an error in front of students, it's not something you want to quickly get out of. You want to show them slowly how you recover from this error. Ask them, what do you think the error is, Really engage them on the error because they're going to run into loads of errors themselves and they need to know how to get out of that. The other thing is demonstrating your tool use. You're coding in your editor, you can show them how you get around the code, how you compile, how you do these kind of things that we take for granted, but people need to learn sometimes. And definitely when you get an error, it's a great teaching moment. And particularly, you get that bit where your brain has frozen, you don't know what to do. It's a perfect opportunity to turn it over to the students. What do you think we should do in this case? And you give them a little bit of time, they may fix the error, or they may just sort of spin round in circles for a little bit. But either way, you've got a bit of time yourself to reboot your brain and figure out what's going on if they can't figure it out for you. All right, so yeah, there is also implicit knowledge. It needs to be taught somehow, and live coding is a reasonable way to do it if you don't want to take time to teach it explicitly. Right. Tip number 4. Tip number 4 is shut up. Okay, that's probably enough. So the issue here is that thinking while listening is difficult. If you're listening to someone talking to you all the time, then it's very difficult to do any thinking. Anyone who has young children, who's got young children here? I do. You probably know about being talked at when your kid comes in and just yammers away at you for 3 hours about Minecraft or whatever they did at school yesterday or whatever their other sibling has done, great injustice, whatever it is, you don't want to hear it because you've got things to think about, adult things to think about. And yeah, it's very difficult to do while someone is talking at you. And it's the same thing when you're teaching programming, right? You need to give people time to think. The problem is you want to help, you want to get in there, and they see they've got a problem, and you want to jump in and help them solve it. So, but a more effective way of doing that is, firstly, take a step back. Give them a little bit of time to sort things out themselves. Then if it looks like they're not going to be able to sort it out, rather than jumping in and helping, you say, give them some prompts maybe for thinking. Just like, when the kids come and say, my brother hit me, you don't just want to go and storming in and, did you hit them? You say, well, why did he hit you? Maybe you can sort it out yourselves, that kind of thing. Hands-off parenting. So give them some prompts for thinking. Like saying, what strategy are you using? So if you use the programming strategies, prompt them, like, is this a structural recursion problem? Get them to think explicitly about how they're approaching a problem so they can do a little bit of metacognitive thinking, or what technique am I using to address this problem? They can be more aware of their own technique and they can formalize it a little bit more. Or perhaps you can give them some bit of feedback. You can say, well, I think your code is wrong here. Just direct them towards where the error is. But then don't tell them the solution. Why do you think that's the case? What do you think is going wrong here? I think this is where it should look. Or maybe just get them to voice their mental models. You could say sort of, explain to me what you're doing, or explain to me what you think is going wrong here. And this is great because it gets them to really verbalize what they're thinking. And once they do that, they might find that it's incoherent. We're often the case where we think we have a consistent model, but as soon as we have to present it, we realize it's full of holes. And that way you get the students to sort of formalize themselves. As much as we would like to be the case, we can't do the learning for the students. We have to let them do that. Job as a teacher is to present material. You need to do that. This sort of completely hands-off approach of just, here's a tool, have fun, doesn't work as effectively as active teaching. But we also uncover and correct flaws in their mental models. So poke at them, prod at them, try to get them more structured in their programming, try to get them to present what they're thinking so you can find out where the problems are and you can correct that. Don't just jump in and say, this is what you need to do, if you can help it. So don't be the oracle, the source of all truth to solving their problems. Okay. Tip number 5 is peer learning. Great for the lazy teacher. This means getting the students to teach each other. Now, one of the best ways to learn is to teach. Why is that? Well, it forces you to really understand the material. You need to know all the nuances, and you need to have that consistent model, the way of explaining it. So, teaching is it's great for this, great for generating a coherent model. And if you can get the students to teach each other, then you're forcing them to develop that coherent model, right? So how can you do this? I'm going to give you 3 ways that students can teach each other. There are lots of ways out there. If you're interested in reading literature, the sort of further resources will give you some ideas. Number 1 is like what I call the hypothesis game. So this works in larger classes where you maybe don't have time to talk to everyone individually. What you can do is you can ask a question, and you can then get students to answer that question, to take a guess. answer that question. And then, this is a bit that makes it better than just getting them to answer the question individually. You can do this, you can just have them voting, like raising your hand for different answers, or if sometimes people have like fancy phone-based systems that people can vote on. It doesn't really matter how you do this, just sort of prompting them to come up with an answer. And then you can get them to justify the answer to another student, and this is the key bit. This is where the learning happens, because then they've chosen an answer and they have to turn to someone else and explain why that's correct. That's when they go, oh, what I'm thinking doesn't make any sense. That model doesn't work. I need to adjust my thinking, or maybe it does make sense. And they can learn from each other. So a time-efficient, simple way of getting people to teach each other. Another programming-specific tool is pair programming. A lot of people do this. Two students, one keyboard, or you want to do mob programming, many students and one keyboard. I've done this in some cases, and it actually works surprisingly well when you have already engaged students. They're all shouting at each other, yeah, do this, do this, do this, and everyone sort of wants to jump on the keyboard. Everyone's really engaged. It can work very well. The key thing here is don't let anyone just like hog the keyboard and do all the typing. Particularly when you have different skill levels, it's very tempting for the more skilled person to say, just give me the keyboard, I'm going to show you how to do it. And then the less skilled person normally just gets left behind. So whoever's not typing must be active, must be thinking, must be engaged, or it's not going to be effective. There's a lot you can say about pair programming. Maybe you've got experience yourself. There is tuple.app, which is a screen sharing application, and they have this pair programming guide, which I think is quite good if you're not experienced with pair programming, going and reading that. And the third technique I want to mention is the famous rubber duck. Who's heard of rubber ducking before? I have. Okay, yeah, so great. So we all know this idea. And this is basically when you don't have someone around to talk to, explain to an inanimate object. That's basically pair programming for one. So you've been forced to make your mental model, vocalize your mental model, and then you'll see all these flaws in it. I think we've all had that experience of maybe writing an email like to a mailing list. I have this problem, I'm trying to do this, and I do this, this, and this, and then you go, oh yeah, okay, I see, you see the error. As soon as you write that email, it's the same thing. It's just really making your thoughts explicit, and then you'll see the errors in what you're trying to do. So very useful for teaching yourself. I recommend doing it. Okay, so those are my 5 top tips, but there's lots more I could say, so I want to give you 5 more resources to go to for further learning. So, 5 further resources. Number 1 is this little paper, 10 quick tips for teaching programming. So it's twice the value of my talk, because it's got 10 tips rather than 5. It's very easy read, and they're very things that are very directly applicable to teaching, very sort of applied stuff, not much on the theory. Yeah, you can go give that a read. It's pretty good. Number 2 is this book called Teach Together by a guy called Greg Wilson. Definitely worth having a read through that book. It's a fairly short book. I think it's 100 and something pages long, but very good content on teaching in general. One thing that all of these resources lack is the things that we can do in functional programming. Functional programming has this strong mathematical model we can leverage for things like the programming strategies I discussed earlier, structure, recursion, algebraic data types. Okay, you're not going to find much of that in the literature, but lots of the other techniques you'll find in resources like this. Greg Wilson, the author of this book, is worth following. He's either writing a new book right now, teaching tech, I think, or maybe he's updating this book. I'm not 100% sure, but either way, I'll be having a read of what he's doing when it's finished. Number 3, how to design programs is the inspiration for our programming strategies. So this is a book in the functional programming world. They use Scheme to teach programming, so lots of lovely parentheses. And this is where I first saw this idea of you can make programming systematic, you make programming repeatable. How to design programs itself is it's quite a big book, and it moves very slowly. So I'm not sure it's something that you'd necessarily want to take directly, but I've taken a lot of inspiration from their approach. So well worth a look if you're interested in that type of thing. So all of those, they tend to focus on programming, moving away from programming into the wider world of education. There's an enormous amount of research out there. And one thing that I like as someone who's not an expert on teaching is this visible learning site. What this is a guy called John Hattie who has done a number of meta reviews of the literature. So that means he's taken lots of studies and he's aggregating the results of many studies, looking at the techniques they look at and trying to work out what's the more effective, what techniques are more effective. And so you can just focus on those techniques. Now, there are some reasonable questions about whether the effect sizes he reports, the numbers he reports are accurate. They're probably overestimating, so he has things where the techniques which supposedly correspond to like a year or two of improvement of someone going like through high school. That seems to me a little bit high, but it's not really important so much as the absolute value, but more the ordering, which is where we should be looking at for techniques that are worth learning. So I found that very useful because it just cuts down the literature a lot. I know these are like sort of the top 10 techniques is probably that I should learn about rather than looking through a mountain of educational literature. The final thing I want to mention is your own practice. If you teach, you're a senior developer teaching juniors or you're teaching some other context, then your own practice is a great way to get better. You need to do this deliberately. You need to really focus on what you've done, reflect on what you've done and say, what can you learn from that? So one of the things I'm focusing on at the moment is getting better at student interaction, at feedback, giving students useful feedback, not jumping in straight away, that kind of thing, or maybe not leaving people for too long. So some of the thoughts in this slide are from my reflections of courses I've been teaching recently. I feel it's something I need to improve on. Okay, so that's the main content of what I wanted to talk about. So what are the conclusions here? Number one is that teaching is a skill. It's definitely a distinct skill from programming. Just being a good programmer does not make you a good teacher, and it's a skill you can definitely improve at, a skill you can learn with a little bit of effort. The other point is that I think teaching is very valuable because it's not really very different from learning. The strategies that make you a good teacher you can also use on yourself to help you learn, and you need to learn all the time. It's something we all have to do, whether we are teaching others or not. Just to recap, my 5 tips are this Notional Machine, have a model of what you're doing, that you can understand what you're doing. The programming strategies to make programming systematic. Remember that there's more to coding than coding, so you need to teach those sort of things. Don't be too hasty to jump in when someone's struggling. Struggling is an essential part of learning. They need to do the learning themselves. And getting people to teach each other is a great way to make their learning more effective. Finally, a shout out to Scala Bridge. If you are interested in getting more experience in teaching, then there are Scala Bridge events running in a number of locations. We've got one in London, and there's one starting up in Bay Area. I think people in New York might be thinking of doing one. Okay, there's one happening there. We had one at Scala Days yesterday. So there's opportunities you can join in to get more experience teaching, or you can start one yourself. You know, all you need is a website, a little meetup page to get students to sign up, and away you go. It's great fun. It's really nice to see people just improving and getting better. For example, from Scala Bridge London, we have 2 students who've come along to this conference and never done Scala before, and now they're coming on to Scala Days, and they've done some great stuff. Thanks. Do consider getting involved. Scalabridge.org is the site, and yeah, that's all I've got to say. Thank you for your attention. That again is contact details. Slides will be going up on the website once I get time to upload them. thank you all for your attention, and if you have any questions now, I'd love to take them. Yes.
So you told us you identified 10 programming strategies and you presented 3. Where can we learn about the other 7?
Okay. There's nowhere public at the moment. We are kind of working on something to make them public. It might be like a paper for some academic journal, because I'm kind of quite interested in interacting with the academic community on this. If it is a paper, it will be open access, so you will be able to, everyone will be able to read it. Yeah.
Great, thank you.
Yeah, you're welcome.
Hi, Noel. Thanks for a great talk. So you talked about implicit knowledge, such as cryptic error messages. Have you tried to make them more explicit for students, maybe writing some documents and so on?
Yeah, you certainly can make that knowledge explicit. So, for example, there are courses out there on using Git. The guy I mentioned earlier, Greg Wilson, has this project called Software Carpentry, which has a tutorial on Git that's probably very good. It can be done. It's work, it's effort, and life is finite. So you have to choose what you're doing. So in the context of, say, Scala Bridge, for example, we had 6 sessions. We had about 2 hours of actual teaching per session. So it's only 12 hours. You consider that's like 2 or 3 weeks of a university course. Not very much time. And if we spend time explicitly teaching Git and these kind of things, that would really take a lot of time away from the rest of the teaching we want to do. So it's just a trade-off there. I think you get the same thing in commercial settings. When we did a training course, normally 2 or 3 days, where you don't want to spend like half a day just talking about using an editor or interpreting error messages. And I'm sure it's the same as well if you're mentoring junior developers, things like that. Maybe you have a bit more flexibility there, but again, it's taking up time. So making explicit is great, but you've got to get the material from somewhere, and you've got to get the time from somewhere. So there's a trade-off in there. I mean, obviously everyone knows Emacs is the greatest editor, and we should all spend time learning it, but for some reason people don't agree with me. So.
Hey, do you have any ideas about how to make rewarding this type of behavior explicit within companies? How companies can make this a behavior that they can encourage?
Right. So we're talking about having a culture of mentoring and teaching and so on. Yeah, that's a really good question, because companies spend an enormous amount of money on recruiting, and many developers, particularly sort of Silicon Valley, move very frequently. So you'd think that people would spend more effort on retaining. I'm not sure I have any great answers there. That's something I think we struggle with, getting people to recognize the value of teaching and mentoring. One way is to put it in terms of recruiting, like how much are you going to spend to recruit a developer? Probably at least 10,000 currency units, whatever those will be. And that is sort of one argument we use with people that say that, people say you can never hire senior developers. Yeah, you can't hire senior Scala developers. So the only real solution you have is to build your own, and by teaching them and training them. And it's probably much more cost effective to do that than to have people leaving and that kind of churn of. So that's one motivation. I think that works with upper management type people who are more concerned about the numbers. You definitely need to have a cultural aspect there. And that's very hard to do, because you need people to say, okay, you need to take time away from stuff that's directly delivering features. You can't have like a 2-week sprint when you're stuck in this kind of mode of continuous 2-week sprints. There's not really any time to step back and learn some more skills. And making this kind of cultural changes is very hard to do. Something I struggle with for sure. I have seen some great organizations really have a strong emphasis on learning. Andreas in the audience comes from one of them. And I may have seen some organizations that just don't care, and they just grind people, and they have a continual churn of people leaving, and they wonder why. So yeah, it's a very difficult problem. I think it's organizational change. I think organizational change is hard. I wish I had a better answer for that. Question down the front here.
When you're showing examples, or especially if you do live coding, what kind of examples do you choose? I mean, we had now the map example. Is that something which is good for beginners? Because it seems very abstract, and do you also ask your students what they want to do with programming, or that kind of stuff? So
I think
keep being excited.
It depends very much on context. So, the example like map on a list or map on an option is something I would use for someone who is new to Scala but expecting to be a commercial developer in Scala, because it's introducing these basic strategies, and it's also explaining to them how a bit of the standard library works. So you understand option because you've implemented it yourself. You know, you've implemented map and flat map or whatever on option. So it's not strange or confusing anymore. You've done it. In the context of the Scala Bridge stuff, where we're teaching people who are new to programming, completely new to programming, not always completely new to programming, some of them are experienced developers, but that's the thing that makes Scala Bridge unique, I think, is these people. We often use graphics, doing pretty pictures there, and that can be quite motivating to them, just to have an immediate, pleasant result, rather than just kind of working on code and seeing text output. Example of some of the students we've had there, we had a fashion designer, we had someone who was an accountant but actually had a history of art degree, and so they really enjoyed this graphical output. That was very motivating to them. They spent a lot of time tweaking with their pictures and so on. So yeah, it depends on the context. If you've got more experienced developers, I think these are basic techniques that people need to learn, but if they're more experienced, they've used Scala a little bit, maybe we'll talk about something that's relevant to what they do. So a lot of functional programming revolves around this idea of interpreters. This gives you a separation between description and action. That's the way that you can manage effects in a functional way, is you don't actually carry out any actions until you go run, like an IO monad, and you say unsafe run sync or whatever. So you might build an interpreter to solve their problem. What's the problem? It might be sort of validation. Maybe you can express validation rules as like a little language and have an interpreter for these validation rules, or something else, whatever it could be, where you could find a case study that's relevant to what their problems are, and show that the techniques come up again and again. So yeah, list is something I can throw on the board, and I expect everyone to be kind of familiar with here. In a company, you'd ask, what kind of problems do you work on? What can we talk about? And take it from there. Okay. Any further questions? Gentlemen over. Are we out of time, are we? Okay, we're out of time, so come and ask me afterwards. Happy to take the question. So thanks once again for your attention, and I hope you enjoyed the talk and the rest of the conference. Thanks.